So our final talk today will be from Natalie Behague from Ryerson, and she'll be telling us about synchronizing times for case sets in Automata. Take it away.
Okay, thank you, Carla, particularly for introducing me and to all the organisers of this conference. Feel free to interrupt me to ask questions. I am somewhat jet lagged, so I may be less coherent than usual, so do ask questions if you need to. Okay, so this is all joint work with Robert Johnson, who is my PhD supervisor at Queen Mary University of London. And we'll be talking about synchronizing times for case sets in Automata. So let's define some of those things. First of all, what are synchronizing automata? So an automaton, pretty simple. It's just a collection of states. I will always have a finite set of states, which I'll usually label 1 to n. And we have a collection of transition functions, which are just functions that act on a set of states. It takes a set of states to itself. And I like to draw my automata like this. So here is an automaton on 4 states. We have 1, 2, 3, 4. And it's got 2 transition functions, f, which takes 1 to 2, 2 to 3, 3 to 4, and 4 to 1, and g, which takes everything to itself except 1 goes to 2. In general, an automaton can have any number of transition functions, I guess, bounded by the number of maps there are from end to end. Okay, so we're going to be interested in words on the transition functions, and a word on the transition functions is just a sequence of transition functions applied one after the other. We call such a word a reset word if it sends every state to the same state. So one way of thinking about this is if you imagine the automaton as a maze. You get dropped somewhere in the maze, and a transition function is like a room that you can step into. So you'll get dropped somewhere in the maze. You don't know where you are. A reset word allows you to do a sequence of moves. Maybe it's like left, left, right, right. That after you've done that sequence of moves, you then know where you are. You kind of oriented yourself within the maze. So in our particular example, if you apply the word G, F, 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 G, F, 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 G, that sends every state to state 2. So try it out. G, F, 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 G, F, 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 G sends 1 to 2. I mean, I'm not going to check through all of them, but if you want to, you can check through all of them and see that whenever you apply this word, so if you start on 2, you end up at 2. If you start on 3, you end up at 2. And if you start at 4, you end up on 2. So this is a reset word. It's worth bearing in mind that not all automata have reset words. So if all of your transition functions are permutations on the set of states, obviously you're never going to have a reset word because you're never going to send 2 states to the same state. So that's a necessary but not sufficient condition. We call an automaton synchronizing if it has one of these reset words, which are also sometimes called synchronizing words. Okay. So the big open conjecture in the world of automata theory is Cerny's conjecture, which is that if an automaton is synchronizing, so if an automaton has a reset word, then it has a reset word of length n-1 squared. And if this conjecture was true, it would be tight. And the example is this example that I showed you before. So in general, we have an n-state automaton. So this is the example for 4, but you have 2 transition functions, one which is a cycle, takes each state to the next state, and one which takes every state to itself except takes 1 to 2. And it's not too difficult to check that in the n-state version of this, a similar kind of word to G, F, 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 G, F, 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 G is a reset word. It's going to be something like G, then F, n-1 times, then G, then F, n-1 times, and so on. And that you can't find a reset word that is shorter. So this particular automaton has a reset word, but the shortest reset word has length n-1 squared. Okay. So what is known about Cerny's conjecture? Well, we can find some upper bounds. So there's a very naive upper bound you can find if you think about this briefly, which is, think about pairs. So a pair of states, if our automaton synchronizing has a reset word, which means that any pair of states can be sent to the same state by some word, how long does it take to send a pair of states to the same state? Well, worst case scenario, you have to apply a transition function, and as you're imagine those pair of states moving, as you apply transition functions, at worst case scenario, you have to pass through every single other pair before you can get to a singleton. So worst case scenario, given a pair of states, you might need a word of length n choose 2 to send it to a singleton. So applying that argument repeatedly, you start with n states, you pick a pair, you find some word of length n choose 2 that sends that pair to a singleton. You look at the image of what you have so far, you pick a pair within the image, find a word of length n choose 2 that sends that pair to a singleton, and so on. And we get this bound as n minus 1 n choose 2 just by repeatedly picking pairs in the image. Now, you're probably thinking, that seems far from optimal, because at each point you just picked a pair that was in the image of what we had so far. But if we have a lot of choices of pairs in the image, we could probably choose a pair to squash to a singleton that didn't take n choose 2 steps to be squashed. That's good instinct. So there's this theorem of Frankel-Pin from 1983, which says if you start with k states, then you can find a word of length n minus k plus 2 choose 2 that sends that set of k states to a smaller set of states. And that's exactly capturing the instinct that when you start with lots of states, you can probably find a pair that takes less time to squash down than n choose 2 steps. So if you apply this with k equals n, you'll see that it takes 1 step to squash down to something smaller. That makes sense, because we know that we can find a word that's not a transition function that's not a permutation. And then if you substitute in k equals 2, then worst case scenario, you might have to do this n choose 2 steps to squash the singleton from a pair. So we can get a better or slightly better upper bound than our naive upper bound by repeatedly applying this Frankel-Pin thing. And if you sum those up, it turns out you get something like n cubed over 6. So this is n cubed over 2, this is n cubed over 6. This is from 1983. The state of the art, barely any better. So the state of the art, best known 2019, is 0.1654 n cubed, which is an improvement on a 6th n cubed, but a very, very small one. And especially embarrassingly small, considering that the conjecture is actually that it's n squared and not n cubed at all. So yeah, so it seems like this is a hard question. So one thing I want to say is, maybe you're now thinking, given that in 40 years, no one has really been able to improve the upper bound very much, maybe n squared is incorrect. So here's some more intuition on maybe why n squared is correct. There are a lot of different families of automata where we know that the n minus 1 squared is the right thing, and these are all kind of different ways of generalizing the Cerny automata or the standard automata that I about before, which give you the type bound. So first one is if the automaton is orientable. That means if there's a cyclic ordering of the states, where every transition function takes an interval within that cyclic ordering to another interval within that cyclic ordering. Another is so that these drawings of these automata naturally look like digraphs, and if the underlying digraph is Eulerian, then the conjecture holds. And finally, if one of the transition functions is a cyclic permutation of all the states, no matter what the other transition functions are, if there's a reset word, there's a reset word of length n minus 1 squared.
One quick question, sir. Are they, in this case, do they get even smaller ones, or they get n minus 1 squared?
So all of these families include our collection of standard automata. So in these cases, that family always gives you n minus 1 squared. There's actually an interesting thing that you don't seem to find all values. So you get like n-1 squared. There's automata with examples where the length is n-1 squared, and then you get automatons where the examples are like n. So that n-1 squared is like n squared minus 2n, right? And then you get ones which are like n squared minus 3n, but nothing in between. So there's like kind of weird spectrum thing going on.
That's cool. So you can show that these things in between, they don't exist at all. People have
no one can show that. Just computer searches suggest.
Okay.
So that's another nice question, like what's going on there. But yeah, so the other evidence for this conjecture being true is that people have done computer searches for lots of small n and not found any counterexamples. Yeah, this is a problem that lots of computer scientists are interested in too, so I kind of trust their computer searches to be probably more thorough than if it was just combinatorics people. Okay, so what am I going to say next? I'm going to introduce you to a different way of drawing these automata. So here's my favorite automata. It's 1, 2, 3, 4 state automata. And a different way of drawing them, I call these a transition graph. You could also think of it as the power set automaton. But basically, I have vertices labeled by each set of states of my automaton. And I divide these into layers. So the kth layer will be k states of my automaton. So here I've got 4 states and then 3 states, all the different sets of 3 states. And then I draw in my how the transition functions act on these sets of states. And this is quite a natural way of drawing them if you're thinking about Cerny's conjecture, because now, remember I explained to you that this had this reset word G, F, 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 G, F, 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 G. You can see that really easily from this transition graph. So you start at the top, you apply the word G, F, 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 G, F, 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 G, and you see that that takes you from 1, 2, 3, 4 down to 2. So that's, once you've drawn this out, it's really easy to spot reset words. It's just that a reset word now is a path that takes you from the top layer to the singleton layer. Another thing that you might spot while staring at this is that the Frankel-Pin thing. So the Frankel-Pin bound says that given any set of k states, we can find a word that takes that to a smaller set of n minus k plus 2 choose 2. So what this is kind of saying is, given the worst thing in the kth layer, we know how long it takes to get to the k minus 1th or below layer. One sort of obstacle that Frankel-Pin has is that it's always talking about the worst thing within a layer. So, for example, if you say going from the pairs to the singletons, it's saying there is a pair that takes 6 steps to be squashed to a singleton. And that's true in this example here. 2, 4 takes 6 steps to be squashed to a singleton. You have to go to 1, 3, and then round, and then there. So it takes 6 steps to be squashed to a singleton. But the shortest path from the top to the singletons, so that's our reset word, doesn't ever have to go through 2, 4. So the fact that 2, 4 takes quite a long, it's difficult to squash to a singleton, doesn't actually impact our shortest reset word. So that is basically the inspiration for this next definition. So we call the k-set rendezvous time is the length of the shortest path from layer k to layer 1. So that's different from the Frankel-Pin thing, because I'm no longer saying take the worst thing in a layer, how long does it take to get to the next layer? I'm saying take the best thing in a layer, how long does that take to get down to a singleton? So it's sort of saying, I no longer care if there are k-sets that are really hard to squash. I just want to know what's the easiest k-set to squash and how long does it take to squash that. So this was introduced by Gonzer and Jungers, who found some lower bounds. So the standard example gives a lower bound of k minus 2n plus 1. So the standard example, if you take like an interval, so you have n states, you take like an interval that takes k minus 2n plus 1 steps to squash down to a singleton. Gonzer and Jungers actually showed, which is kind of surprising, that in this, for the k-set rendezvous world, the standard example doesn't always give you the best lower bound. So they found an example where the number of steps to squash down from a triple to a singleton, even when you got to choose your best triple to squash your singleton, took n+3 steps, which is only 2 more than the standard example, but it's kind of interesting that the standard example isn't giving us the best bound. Okay, what about upper bounds? Well, so we can do a stupid thing. We can apply Frankel-Pin directly. So it's k-set rendezvous time. We can pick something in layer K that takes 1 step to get down to the next layer, just something with an arrow down to the next layer. And then apply Frankel-Pin from there on in. So now we say we're in layer K-1, maybe we're in the worst thing in layer K-1. How long does that take to squash the next layer, and so on and so forth. And you get this thing that's like K-2 and K-2 over 2 n squared. But that doesn't really capture the flavor of what we actually wanted with this k-set rendezvous stuff, because we're just using Frankel-Pin and except for the first step. So our new results, Amy and Robert, showed that okay, so the first result is this theorem that shows for fixed k and n sufficiently large, you can get the floor of k-1 over 2 n squared over 2. So if we go back, this is k-2 over 2. This is more like k-1 over 4. K-2 over 4, depending whether k is odd or even. So it's half as much as what the Frankel-Pin gives. And this is actually quite a simple argument. It's just using Frankel-Pin, but sort of Frankel-Pin from the top and Frankel-Pin from the bottom, and then combining the two. That's very vague, but that's how I think of it. You might notice that if you substitute k=3, which is kind of the first interesting case, so k=2 is just going from a pair to a singleton. We know there's a pair that takes 1 step to squash a singleton. k=2 is not interesting. The first interesting case is k=3. You might notice that this k=3 case, this doesn't actually give you an improvement on Frankel-Pin. So this gives you n squared over 2. Frankel-Pin also gives you n squared over 2, because we know we can pick a triple, it's 1 step to squash down to a pair, and then worst case scenario, we have to go through all possible pairs, which takes n choose 2 steps. So we were also interested in focusing a little bit more on k=3 and seeing if we can improve this n squared over 2 bound for k=3. Turns out you can. So here's the bound. The rendezvous number for 3 is bounded by 3 minus root 5 over 4 n squared, which is about 0.191. So that's quite a lot less than a half. So that's fine. And then that approach that we took for 3 can be generalized to give some bounds, better bounds for 4 and 5 as well. So for this bound gives you n squared over 2, so this is a slight improvement. And for 5, this bound gives you n squared. So this is, unfortunately, while this approach can be generalized to larger k, it doesn't continue giving an improvement on this stuff. So when k=6, this bound starts beating this approach. So I think you would need to have some extra idea to deal with larger k cases. So I have a limited amount of time, so I'm just going to focus on the slightly more involved proof, which is theorem 2. So how does this proof work? So remember what we're trying to do. We're trying to see if we can pick off a best triple, and we want to know how long it takes to squash to a singleton. So what I do is I define, I could end up splitting into 2 cases depending on the rank of words. So the rank of a word is the number of points in its image. And we're going to let R be the minimum rank over all words of length at most n. So you can think of, if R is small, that means all words of rank, that means there exists a word of length less than n, which has a small number of points in its image. So it sort of sends everything down to a small set. And if R is big, that means that all words of length at most n have quite a lot of points in their image. we have these two claims, depending on whether R equals small or whether R equals big. So the first claim, I think, is possibly the less surprising of the two. The first claim says, if R is small, then we can find a word that sends a triple to a singleton of length not that big. And you can think of that as saying, well, so R equals small, so we can find a word which sends all n states down to quite a small set of states. Therefore, it seems likely that we can find a triple that gets squashed down to a singleton in not too many steps, because we have this word that squashes quite a lot together. I think perhaps claim 2 is the more surprising one. So claim 2 is sort of saying if R is big, then we can also find a word that sends a triple to a singleton in not too many steps. And the way that this second claim is proved is to think, so R is big, that means all of my words of length at most n have quite a lot of points in their image. So if I think about all the pairs that can be reached from a triple in at most n steps, there are actually quite a lot of those. Lots of pairs can be reached from a triple in at most n steps. Basically because all my words of length at most n have quite a lot of points in their image. So I know that some triple squashes down to a pair, and I know sort of that pair gets sent to a lot of other pairs. And there's just a lot of pairs that can be reached from a triple in not so many steps. So then once you have a lot of pairs that can be reached from a triple in not so many steps, that's where this bound comes from. It's then saying, well, pick of those pairs that don't take very long to be reached from a triple, pick the one that takes the least time to get squashed to a singleton. The idea behind this anyway. Okay, so that's like very vague overview of the proof. Then we just combine, then we just combine these two claims. So this is increasing with R, this is decreasing with R. So you just say, well, worst case scenarios where these two things are equal, solve for R, you get a quadratic, and that's where this weird square root thing comes from. Okay, so that's the results and a sort of outline of one of the proofs at least. So what open questions are there? Well, one open question I sort of touched on already is that this approach, I said, it generalizes to k equals 4 and 5 and gives us improved bounds. And you can generalize it to greater k, but it stops giving you improved upper bounds. So I think if you wanted to do something for greater k, you would probably need to not only deal with the case where R is small and where R is big, you probably also want to have something to control the case where R is in the middle. Because that's where the problem lies. So could we generalize this to get improved upper bounds for k greater than 5? But it actually, like, we conjectured that this isn't even particularly strong. So our bounds is like 0.191 n squared for k equals 3, but we have no reason to believe that it couldn't be some constant times n for k equals 3 to get from a triple to a singleton. So I mentioned before that the best lower bound for getting from a triple to a singleton is n plus 3. So there's no reason to believe that it couldn't be like 2n or something. Okay, so that's all talking about this k-set rendezvous time. It's worth bearing in mind the worst triple. So that's what Frankel-Pin were considering. So what do I want to say? So the open questions about k-set rendezvous time, if you do them for a fixed k, they don't immediately give you anything towards Cerny's conjecture. Obviously, you hope that they give you tools and techniques that can then be generalized to Cerny's conjecture, but they don't sort of immediately spit out anything. What's nice about looking at instead the worst triple, so this more Frankel-Pin idea where you're looking at the worst thing with a layer, how long does that take to get squashed down? If you can improve the bounds for that, then you immediately get an improvement on the n cubed over 6 general upper bound for Cerny's conjecture. So if you could find some c less than 1, such that for any triple, for the worst triple, you can find a word from the triple to a singleton of length cn squared, then immediately you could do the same thing as the Frankel-Pin approach, but rather than one layer at a time, you're sort of jumping 2 layers at a time, and the n cubed over 6 would improve to like c over 6 n cubed. So I think these are attractive because this k-set rendezvous time stuff has been less studied, so there's possibly more stuff to go on here. This stuff has been much more studied, but it's attractive in the sense that getting something here would immediately give you something for the general terms. Okay, I think that's everything I wanted to say.
Good.
Thanks very much. Oh, maybe a question already, but go ahead.
Yeah, indeed. So when Shitov proved the best bound, he did this by answering this question, or he had a different method?
Shitov didn't use rendezvous times. No, Shitov. So Shitov's approach was so basically the approach of Shitov is to say from you think of the going. You have to go from the top layer right down to the singleton layer. So Shitov's approach from halfway point downwards just use Frankel-Pin. It's never going to get an improvement on something n cubed. But for the top half of the going from sort of the top level to halfway point, you got a small improvement by some kind of saying, well, either we have this is small, either we can get there in a small step or some. There's some kind of either or case where either if you don't get there in a small number of steps, you can sort of say, oh well, this other weird thing happens where you can get. Yeah, it's slightly complicated. It was actually, I can't now remember the names, but this other authors sort of introduced this approach and should have then like fixed up the constants to make it as best as possible. But yeah, it's essentially building off Frankel-Pin rather than using any of this best case stuff.
I was just noticing because if you prove C smaller than 1 but larger than 0.993, something like this, then you don't improve the best bound known.
Mm-hmm. Yeah, but no, that wasn't done using this approach. It was different.
Do you have any other questions?
Maybe let's first thank
yeah.
Natalie.
Oh, sure. Let's do that.
I was actually wondering about a thing where, so they're now looking at going from, say, the third layer to the first layer. You could also, of course, look at going from the fifth to the third, etc. So is there any kind of relation? I guess in the boundaries, the behavior can be quite different, but is there any kind of behavior on how these times?
Right. So you can use going from the third layer to the first layer as a upper bound on going from like the fifth to anytime you're sort of jumping 2 layers, the third to the first will give you an upper bound on that, and so on and so forth. But you're right in that going from fifth to third could be easier than going from third to first. We didn't specifically look at that, mostly because we were just focusing on 3 to 1, and therefore, like, I mean, 3 to 2 is easy and 2 to 1 is easy. So 3 to 1 was like the first hard case. But yeah, it was very natural to ask about going from layer K to layer K minus L. So,
I guess I was also wondering if there were any kind of symmetries there as well, where, yeah, maybe if you take n large enough and you go somewhere in the middle, that's the times can't differ too much or something. But I guess that's maybe it hasn't been studied much.
Yeah, this case set stuff, this rendezvous stuff, is kind of new. It's a kind of new approach. So I think there's lots of avenues to explore.
That's very nice.
maybe I could just ask a quick one. So do we know something of the complexity? I assume we should, given an automata is synchronizing, just deciding whether it has a particular length reset word.
I don't know. So I'm not the person to ask about complexity stuff.
I
so
actually
I don't
looked
know.
this up at some point. It's NP complete, and it's also
It is.
yeah, and it's also I think the fixed, because I was thinking about looking at the fixed parameter tractability as a question for students, but that has also been solved, and also for like any question I could come up with had been studied there as well.
So deciding if it's synchronizing is also NP complete, I assume? Or...
Well, yeah, I think that the question, is there a synchronizing word of length? But maybe even just the question, is it synchronizing, might be hard. I don't know.
No, you can check if an automaton is synchronizing just by looking at so necessary and sufficient to be synchronizing is that every pair of states can be synchronized. So I think you can actually check if it's synchronizing.
Yeah, so then I guess it's, yeah, just a stronger version of you're given a length, and yeah, can you do it in, is there a reset word of that length?
I have also a question. What if we put some restriction on the number of these transition functions?
Well, it still seems to be hard. Some people play around a lot with just 2 transition functions. So one transition function is trivial. If there's one transition function, if it's a permutation, there's no reset word. If it's not a permutation, but there is a reset word. Oh, so I guess I said that wrong. If there's no reset word, there's no reset word. If there is a reset word, you can show that actually you can just do it in like n steps or something.
Yeah, that's clear.
But if there's 2 transition functions, it's already hard. And all of our examples and lots of the examples in the literature, including the standards, have just 2 transition functions.
So even for 2 transition functions, this Cerny's conjecture is not verified.
Yeah, it's wide open. Exactly.
That's really impressive. How complicated it can get.
Mm-hmm.
We have time for another question, if there are any.
Does it actually get easier if you have lots of transition functions?
Well, I'm sure you could argue not. Like, you could maybe just say, well, if you had the same transition function many times, but I don't know. I think like a lot of the research is focusing on either the general case or like 2 transition function case. So I don't know anything about like if you have lots of that helps. If you have all of the transition functions, then it's easy. So.
Yeah, so maybe that's what I thought, like lots of distinct ones, but yeah, it's not clear, I guess.
Okay, thank you so much. Let's give a round of applause to Natalie again.